Hello. So we are today going to talk about sampling distributions with means, with numerical data, where we care about the means. So we'll talk about the parameters, meaning the standard even deviation, mean and standard deviation for a sampling distribution for numerical data. We'll talk about how do we know whether that sampling distribution is normal, and then we'll calculate and interpret some probabilities. So I started here with a kind of warm-up example. So the manufacturer of a certain brand of aluminum foil claims that the amount of foil on each roll follows a normal distribution with a mean of 250 and a standard deviation of 2. We want the probability that one randomly selected roll has an area less than 248.5 square feet. So we're finding the probability for one single roll. So I want you to think for a second about how we might solve this problem. Basically, this one is really because it's just dealing with one. We're not talking about a sample. We're not talking about a sample statistic. We're really just dealing with one roll of foil out of the entire population of rolls of foil. This is something we can do with just a regular old normal model like we did back in Unit 4, whenever it is we learned that last semester. All right, so I'm finding just the probability that X, that area for one roll of foil, is less than 248.5. I have my normal model that they told us was normally distributed. I have a mean of 250, and then I can find a z-score. Obviously, my 248.5 is below this somewhere. We don't know how far below. I mean, it's pretty close, but in terms of its standard deviation. So I'm going to find my z-score. So my observed value of 248.5 minus the mean of 250 divided by 2 square feet gives me a z-score of negative 0.75. So it's not very far away at all. It's probably even closer than that. And then we want less than that. So I would go to my z-table. I would look up a z-score of negative 0.75. I would find that probability, and I would get around 0.2266. So that is a regular old numerical data using a normal model to find a probability. And that kind of leads us into this particular lesson. Unlike with proportions, like we did in the last lesson, with means problems, our original population distribution had a mean, had a standard deviation, and if we have a normal model, if that original population was normal, we could use a normal model to find a probability for individual pieces or parts of our population. With proportions problems, my original population is not necessarily shaped in any particular way. It's just a proportion. What proportion of the people did that thing? So it kind of works out a little bit differently. We have to be a little bit more careful with means problems. So for example, if I were to take that same kind of problem stem that we started with and now ask, what is the probability that a random sample of 10 rolls has a mean area less than 248.5 square feet? Well, this is now a different question because I'm no longer dealing with individual rolls of foil. And that 250 with 2 square feet normal model that I use to find a probability based around a single roll of foil is not going to help me with this sample of 10 rolls of foil. Now that I'm talking about a sample, specifically a sample mean, I cannot use the original normal distribution. I have to think about what is the sampling distribution for samples of 10 rolls look like. That's what I'm dealing with. So because we're being asked to find the probability for a sample mean, we have to have a sampling distribution in order to answer this question. So I'm going to skip this example for now so that we have time in this video to get to the further examples, but just know that I did and will post a separate video that goes through this example using the same procedures that we will do in later ones. So again, as a reminder, a sampling distribution is when we have a collection of a large number of sample statistics. So kind of our key is, are we dealing with a sample mean or a sample proportion? Are we being asked about the probability around a sample mean or a sample proportion? Because if so, then we need to think about a sampling distribution. And again, the reason these are important is because it gives us an idea of what is typical for those sample means or sample proportions, and it allows us to compare a specific sample statistic to what that group of sample statistics looks like or is typical. So just to demonstrate, we're going to get into some of the rules and assumptions and conditions and steps for sampling distributions with means, but I wanted to do a quick little demonstration with an app. So I'm going to actually go back, and I want to go to this website and talk through a couple of things. So this is a website that just has a whole bunch of random data. I'm going to pick this one right here, which is the words in the Gettysburg Address. And I'm going to do some sampling. So right now I have this set at taking one sample, and it's going to be a sample size of 10. So it's going to pick 10 words randomly from the list of words in the Gettysburg Address. I'm going to say draw the sample. Right, and what it does is it shows me like what were the actual length of the words in the sample that I chose. It gives me that mean of the length of those 10 words, and then it puts the mean on this new graph over here. And I can keep doing that. I just picked a second sample. Its mean is up here at 4.3. So over here on the left side, you can see this is a histogram of the length of all of the words in the Gettysburg Address. So this is our population distribution. So when we pick random words from our population, this is the population that it's coming from. So I could continue to do this, right? I could continue to draw samples one at a time. This is a sample size of 10. Just keep going. But I'm going to make this a bit faster. I'm going to have this computer program take a sample of 1,000 different samples of size 10, because I want to kind of see what this sampling distribution over here looks like in the end. So if I draw those 1,000 samples, I can kind of see, all right, what that distribution now looks like. So I have it using the same scale as my population distribution, just so we can really truly compare the difference. So you'll notice with this that our shape has changed slightly, but also more obviously our spread has changed. So our original population, the length of each word went from about 1 or 2 probably up to a little under 12. But now over here, we're dealing with the average length for 10 words at a time. And it goes from a little under 3 as an average to a little above 6. So my spread has gotten way smaller, but also our shape has changed a little bit. So notice that over here, it's very, very clearly skewed to the right, whereas over here, it is a little bit closer to what we would call normal or symmetric. Right? So I could keep doing that, but I also want to kind of see what happens when I take larger sample sizes. So let's say I have a sample of size 30. Again, I could take this one at a time. So now we've got 30 different words from the Gettysburg Address, and then there's the average. There's another one. There's another one. And already we can see that these averages are generally much closer together than they were on the last round. So let's go ahead and do 1,000 different samples of size 30. And there is all of those averages put together. So again, I can see there's a huge difference between my original population of all the individual word lengths, and now this is the average for groups of 30 word lengths. So again, much, much smaller spread, even smaller than the last one. We're still going from about 3 to 6, but notice those bars are really, really short. So most of the data is kind of in the 4 to 5 range, actually. And again, our shape has gotten much more closer to what we would call symmetric or roughly normal, right? And we can kind of do this for pretty much any distribution you could think of, right? I could pick, here's something that starts off more as a normal distribution. Here's one that's very skewed. This one might be an interesting one. So again, samples of size 10 from this distribution. You can see how that changes it versus samples of size 30. So this is a really good website to kind of play with and really mess with the sampling process and how that affects our sampling distribution when we're dealing with means. So I'm going to go back over here to my slideshow. It's thinking, and really kind of put some context to that and put a summarization on it. So a population distribution is kind of our original distribution for the individual values of our population, whatever numerical values we're dealing with. So our population distribution could look many different ways. In this case, I have one that is what we would call uniform. And then in a minute, I'll show you one that is more skewed, etc. So depending on how we start, all right, our sampling distribution might look different. And remember, sampling distribution is I'm taking many, many, many samples of the same size, and that's sample distribution of sample means. So if I take a sample size of 2 repeated times from this uniform block distribution, that sampling distribution of means is going to look something like this. Whereas if I take a sample size of about 25, my sampling distribution looks like the one on the bottom. So you can see that change in not only the spread of the distribution from population to sample size 2 to sample size 25, but also in the shape, right? We started off very blocky. The second one is more like a triangle. And then by the time we get to the third one, it's looking more like what we would call normal or symmetric. Here's a graph that starts off very, very skewed. There's what it looks like with a sample size of 2. So repeated many, many samples of size 2 from that population. And then here's what that looks like with a sample size of 25, right? So we can kind of, again, see that change in spread. It's getting smaller and smaller, but also the shape is going from something that's very, very skewed to eventually, with a big enough sample size, something looks very, very normal. And then there's one that starts off normal. With a sample size of 2, it's still normal, but smaller. With a sample size of 25, it's still normal, but even smaller. So there's a couple things we can get from this. Some facts that we can know about sampling distributions and how they work. One is that the spread decreases, means the graph gets narrower as sample size gets bigger. And we notice that with proportions problems too. As our sample size went up, our spread decreases. It gets more squished in. So that's one thing that's still true. The second thing that's true and may not be as obvious from here is that the mean of our original population pretty much stays the same for any sampling distribution, no matter how big our sample size is or how small our sample size is. So the mean is pretty much the same as I go from population to sampling distribution to sampling distribution. But the third thing, and this is going to be the important part in terms of our assumptions and conditions, the third thing that happens is shape changes. So the bigger our sample size, the more our sampling distribution is going to approach what we would consider a normal model. And in fact, when sample size gets to about 25 to 30, we usually say 30 to be safe, that distribution for the sample means should look roughly normal no matter what my population started as. So we see that all 3 of these that started off as a population distribution at very different shapes end up looking, all 3, pretty roughly normal by the time we got to sample size of 25. So what this is called, all those things that I just went through, is called the central limit theorem. Basically, the central limit theorem says that the mean doesn't change when we move to sampling distributions. It says that as sample size increases, spread decreases. But it also says that when our sampling size is large enough, and usually we mean around 30, the distribution of sample means, our sampling distribution, will be roughly normal, even if the population was not normal. And that's really, really important to know. Remember how we talked about in the last lesson that we really, really want to know whether our distributions are roughly normal, because if they're normal, then we can use the z-table and we can find probabilities really simply. Well, this is how we do that with a means problem. We look at sample size, and if sample size is big enough, it's around 30 or more, we know that our sampling distribution will look roughly normal no matter what our original population was doing. So let's go ahead and move to our facts, numbers, assumptions, conditions for a means problem. So these are our formulas that came from our formula chart, just like before. This tells us what the mean of a sampling distribution is and the standard deviation of a sampling distribution for a numerical data problem, a problem dealing with means. So our first one, I'm saying the word mean a lot, so hold on. This first one for mean, it says mu x bar equals mu. So mean of the sample means is equal to the population mean. The mean of the means is the mean. It's basically what it says. So in other words, the mean of that population distribution pretty much stays the same as we move into sampling distributions. Our standard deviation formula basically says to get the standard deviation of the sampling distribution, take your original population standard deviation, that's what that is, sigma, and divide it by square root of n. And again, we need to know the shape of that sampling distribution, and more specifically, whether the shape is normal or not. And that's what the central limit theorem helps us with. So let's look at our assumptions and conditions for a sampling distributions problems with means. First two are going to say exactly the same as for proportions. So we still check that we have a random sample to avoid bias, same as with proportions. And we still check that 10% condition to check for independence between trials, same as for proportions. But our third one is a little bit different. This is the one that checks to see, is our sampling distribution roughly normal? And there are actually two ways that I can check that. The first way, if your population distribution is normal, and that would be told to you in the problem. If they tell you in the problem stem that the distribution of word links in the Gettysburg Address is roughly normal, then we know that the sampling distribution is going to be normal no matter what. If it starts off normal, it's going to stay normal. So that's one way to check this condition. If you know that the original population is normal, you can just say, given population distribution is normal, done. Okay. But if we're not told that, or if we are very specifically told that the population is skewed or not normal or something, then we need to go to sample size. And that's where we can use that central limit theorem that tells us as long as our sample size is bigger than about 30, we know our sampling distribution will be roughly normal, even if our population distribution wasn't. So two ways to check it. Either we know the population is normal, or we have a sample size bigger than 30. So one or the other of those is enough to check this condition. You don't have to check both. That's the whole point. But if neither of those things is true, then we wouldn't be able to use the normal model to find a probability. We have our same basic steps for solving these types of problems, just like we did with proportions. Our formulas are a little different, and one of our conditions is a little different. But other than that, we are basically doing the same thing as we did before. So let's go ahead and jump into that. So our example for today is dealing with movies. So the number of movies viewed during 2019, I had to be very clear about that because 2020 is a different world in movies. By students at a large high school has a mean of 19.3 movies with a standard deviation of 15.8 movies. However, the distribution for numbers of movies watched is very skewed to the right. In other words, most people watch kind of a small to moderate number of movies, and then there are a few people who watch very, very large numbers of movies, and it creates this very skewed right distribution. So if we wanted to find the probability that one randomly selected student watched fewer than 12 movies in 2019, can we calculate this probability using the normal model? One student is not a sampling distribution. Or if you wanted to think of it as a sampling distribution, sample size is 1. So with one student, we're dealing with the original population distribution, which is not normal. It's skewed to the right. So would it be appropriate to use the normal model here? No, because our population distribution is not normal. So we can't use that model to find probabilities for individual students. So we can't do that, right? We would have to have a sample size in a sampling distribution problem with dealing with sample means. We would have to have a sample size of at least 30. So if this problem said it's a probability that 30 students watch an average, a mean of 12 movies or less, that we could do. Part B says if we were to take one random sample of 80 students what would be the shape of the distribution of numbers of movies watched? So one sample of 80 students. And then you're like, okay, 80, that's bigger than 30. That'll be normal, right? Not quite. Okay, so this is actually not a sampling distribution. If you remember back on the definition for sampling distribution, I had written it's a sampling distribution, not a sample distribution. So we have to be really, really careful. We should be talking about sample means, or with proportions, sample proportions. We are not talking about the mean for these 80 students' movie watching habits. We're just talking about these 80 students' number of movies they watched. Right? So this is just one sample of students. There's not actually a mean. So it should mimic the shape of the population. Let me show you what I mean by that. So if I have a population distribution that's skewed to the right, like this one, and I just take one sample like this. So I just took one sample and put that numbers for those 80 students on a new graph, right? That is a sample distribution for one sample. And the bigger my sample size, the more it's going to look like the original population, because all I'm doing is taking those 80 students, numbers of movies they watched, and putting those on a new graph. There's nothing happening with the means. It's not a sampling distribution, so that central limit theorem doesn't apply. Right? Whereas if I take many, many samples of 80 students from that population, and for each of those many, many samples, found the mean number of movies watched for each sample, put those means on a graph like down here, that is called a sampling distribution, and that's when that central limit theorem applies. As sample size increases, the shape starts to look more and more normal. So just be really careful. What I like to say here is that the magic is in the means, right? A distribution doesn't just suddenly become normal because we take a large sample. It's the process of taking the mean of many samples that creates that shape difference that we see with central limit theorem. So be careful, read carefully. We should always be dealing with the sample means in order to use our rules for a sampling distribution. So now let's go ahead and see if we were going to find the probability that a random sample of 35 students watched an average of less than 12 movies. Can we calculate that probability? So now, original population is still skewed to the right, but now my sample size, and we are talking about sample mean because it's average, we're now dealing with a sampling distribution that has a sample size of 35, which is greater than 30. So yes. So even though my population distribution is not normal, it's skewed, since our sample size here is greater than 30, we know that the sampling distribution for sample means will be roughly normal. So if I'm trying to find a probability based around a sample mean number of movies watched, which I am, I can do that using the normal model. So let's actually do that. Let's calculate that probability. So now is where we're going to follow those 4 steps. Those 4 steps I gave, like we did last time, are for sampling distribution problems, sample statistics, sample means, or sample proportions. So first step is to check our conditions and assumptions. So first, we were given a random sample of 35 students. So no bias involved here. Second, we're going to assume that our sample size of 35 is less than 10% of all students at the large high school. That checks for independence between trials and makes sure that things don't change too much as we pick our sample. And then our third, check for normality. Right? Remember, there were 2 ways. One way is population is normal. It's not. Second way is my sample size bigger than 30? Yes, it is. So even though my population distribution is skewed right, because n is greater than 30, sample size is greater than 30, we know our sampling distribution is roughly normal, and that's the central limit theorem. Second step is to find the mean and standard deviation for our sampling distribution. So our mean formula, mu x bar equals mu. The mean of the means is the mean. So our original mean of 19.3 from the population is still our mean for the sampling distribution. So the mean of the means is the mean. Means is the same. Standard deviation formula for our sampling distribution says we're going to take the original standard deviation, which is 15.8, and divide it by square root of n, which is 35. So 15.8 divided by square root of 35 comes out to about 2.67. And just like we did in the last lesson, be careful with rounding. The more you round or the shorter you round your number, the more off your final answer will be. I will say it's not as big a deal with these numbers because our numbers here are overall a lot bigger. With proportions, we're dealing with numbers less than 1. So those decimal places tend to make a difference. But with this one, it won't matter as much, but still don't round too much. Third step is to use our normal model to find our probability. So the probability we wanted was that the sample mean for 35 students is less than 12 movies. So we want our X bar, our sample mean, to be less than 12. So thus 12 becomes our observed value. I'm going to go ahead and draw my normal model, mark off my mean of 19.3. And then obviously we know 12 is less than that, but how much less? Is it close? Is it far? That's what the z-score is for. So our z-score, observed value 12 minus 19.3 is the mean, divided by 2.67 standard deviation, gives me a z-score of negative 2.73. So almost 3 standard deviations below the mean is where 12 ends up, which is pretty far away. And then we want less than that. And then, as always, I would go to my z-table. I would find 2.73. I'm sorry, negative 2.73. I didn't get the negative over here. So negative 2.73, and then we would find that probability. And because our z-table always gives me less than, I wouldn't need to do anything to that answer. So I get 0.0032. Pretty unlikely, right? If the true average number of movies watched is 19.3, to find a sample of 35 students whose average number of movies watched is all less than 12 would be really unlikely. Okay, maybe I can watch or find one student who watched less than 12 movies, but to find randomly 35 students who collectively watched an average of less than 12, very unlikely. So interpreting that probability, there's about a 0.0032 or 0.32%, very, very small probability that a sample of 35 students watched an average of less than 12 movies, or that the sample mean number of movies watched for those 35 students is less than 12. There is, like I said, that example 1b, which is a very similar problem to this, is going to be in a separate video. So if you want one more kind of going through the full steps of the sampling distribution problem, it is there. Otherwise, I will see you guys next time.